morning again. This is Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. Today we are going to continue to discuss the reactions of alkene. Last class, I briefly gave you the ideas about the different types of reactions of alkene. Generally speaking, you can have three types. The first one called addition reaction, a second one called oxidation reaction, the third one called polymerization reaction. Regarding the addition of your alkene, you can see we have 6 or 5 different types. The first one called the hydrogenation reaction, meaning your alkene can be reacted with your hydrogen to form alkane. Second reaction called the hydrogenation reaction. As we learned, usually HCl, HBr, the more commonly used. This reaction related to the alkene reacts with the hydrogen halides. So this reaction you need to pay attention. You may have 2 different types of products. One is called Markov-Nikov's rule. Another one called anti-Markov-Nikov's rule. The third types of addition reaction is called hydration reaction, meaning your alkene is going to react with your water to form an alcohol. The fourth type of reaction will form the dihalides through the alkene to react with the halogens. Again, your chlorine, bromine, chlorination, bromination is more commonly used one. And then if you have the alkene reacted with these halogens in presence of water, in the existence of water, you are going to have another reaction called halohydrine reaction. When we are discussing about the hydrogenation reaction, I also mentioned some reaction which is followed by anti-Markov-Nikov's rule. So this lecture we are going to show you the anti-Markov-Nikov's rule, which is going to produce the alcohol with carbon with fewer hydrogens will be added by the hydrogens. So you call the anti-Markov-Nikov's rule. I will show you the different types of reactions. The second classification of a reaction of your alkene will be called oxidation reaction. We have 2 types of oxidation reaction. The first one called epoxidation. You are going to form a 3-numbered epoxide. So inside you have oxygen in the 3-numbered ring. Oxygen, carbon, carbon bond. Carbon-carbon form bond. 2 carbons form bond with oxygen. You call the epoxide. Under a very strong oxidizing agent such as peroxyacetic acid, peroxycarboxylic acid. The second types of oxidation reaction is called ozonolysis. This reaction even stronger, meaning you have very strong oxidizing agent. The carbon double bond will be cleavaged. Carbon double bond will form 2 carbon-oxygen bond, carbon-oxygen bond. Therefore, you produce carbonyl compounds. The very last type of reaction we call the polymerization reaction. So this reaction usually is undergone the free radical reactions. We are going to show you some mechanism about this polymerization reaction. So again, let's come back to our hydration reaction. Previous class we mentioned whenever you have your water added with alkene under the strong acid as a catalyst, you are going to produce a Markov-Nikov's rule. If you have a boron hydride added to your alkene followed by oxidation reaction in the basic solution, you are going to produce an anti-Markov-Nikov's product. So again, in this reaction, so you are going to have your hydroboration reaction and then followed by oxidation reaction. Hydroboration reaction is the addition reaction of your boron hydride to your alkene. You are going to form an organoborane. This organoborane is going to be subjected to the oxidation reaction. The oxidation reaction of your organoborane will replace the boron substituents. This boron substituents will be replaced by a hydroxyl group. Oxidation replaces boron substituents with hydroxyl substituents to form an alcohol. There's two major steps. You are going to produce an anti-Markov-Nikov's product. What's going to happen? So you essentially have these three major steps. So first of all, you are going to add in your boron into your carbon double bond. This case, the least substituted carbon in your alkene will be subjected to reaction. You produce a you form a borane product, and then this organoborane will be subjected to the oxidation reaction under hydrogen peroxide and sodium hydroxide. So you produce a 1-decanol. And then the reaction, normally you can simply write it down. You have a alkene, carbon double bond. The carbon with more hydrogen will be bonded with your OH, hydroxyl group. This reaction is considered anti-Markov-Nikov's rule. So this hydroboration oxidation reaction is not only a regioselective reaction, but it's also a stereochemical selective reaction. So what does that mean? Meaning the hydrogen and your hydroxyl will be added in a syn orientation, or when you have your substituents, this OH alcohol will be added to the opposite or trans position of these substituents. This reaction you also need to know, you need the boron hydride such as B2H6 under a dichlamide as your solvent, and then you also need an oxidizing agent such as hydrogen peroxide in the basic solution. So you produce a anti-Markov-Nikov's rule. This anti-Markov-Nikov's product is also give you a trans position. The trans product will be more dominating, such as this case, your trans 2-methyl-cyclopentanol is going to be 86% in the product yield. You may have a question, what's the mechanism? Why this reaction occurs as an anti-Markov-Nikov's rule? Follow the anti-Markov-Nikov's rule. So generally speaking, again, if you have this, let's see, for example, 1-methyl-cyclopentane. So this carbon 1, you have no more hydrogen. This carbon 2, you have one more hydrogen. Theoretically, when you have your hydration reaction, this carbon will be subjected to the OH. However, anti-Markov-Nikov's rule, your hydrogen will be added to the carbon with fewer hydrogen. What happened? So in other words, this borane is going to be added to the carbon with more hydrogen. That's your first step. You produce a borane. Addition of your boron hydride through formation of a 3-numbered pi complex intermediate. What happened in your alkene, in this double bonded carbon? So you have a pi electrons, 2 pi electrons. They are coming from your pp orbital, pz orbital, which is not participating in hybridization. This 2 electron is going to occupy the boron p orbital, which is empty. Therefore, you form something we call the pi complex. This case will make your double bonded carbon partially positively charged, make your boron partially negatively charged. This partially negatively charged or partially positively charged intermediate is not stable. It's going to subject to the pi complex rearrangement from a 3-numbered ring to a 4-numbered ring. Which one is going to be involved in your boron, organoborane? This boron hydrogen bond will be involved in this rearrangement. So you are going to start forming carbon hydrogen bond, start forming boron hydrogen bond. So carbon hydrogen, boron hydrogen, these two bonds is going to competing with each other. Carbon is more electronegative, therefore this bond is going to be break up. This carbon boron bond break up, carbon hydrogen bond will be formed. Simultaneously, this double bonded carbon start weakening. This double bonded pi bond will be break up. You form a carbon boron bond. Due to you losing one proton, so you have BH2. You form a boron. This boron is going to be further oxidized. So this BH2 boron substituent will be simply replaced by your hydroxyl. So what's the addition? How this reaction is going to occur? So you are going to essentially through, I will consider, you can say, 4 steps. First step is called the deprotonation. Second step called the nucleophilic attachment. Third one called the carbon migration or pi complex rearrangement, and then hydrolytic cleavage. So let's take a look. Deprotonation meaning you have your hydrogen peroxide and your hydroxide. They are going to form a protonation processing. What's going to happen? This proton from your peroxide is going to be attracted by the lone pair from your hydroxide. Therefore, you form a water molecule, and then you form a hydroperoxide negatively charged ion. This is a negative charged ion is going to attracted by the boron, organoborane. From the previous step, you form BH2. This BH2 start bonding with your oxygen, so you form this intermediate. This intermediate is going to subject to the carbon migration. What's going to happen? You have carbon boron bond. You have boron oxygen bond. Your carbon is going to be attracted by your oxygen. You again form a 3-numbered ring. Carbon oxygen bond starts to form. Carbon boron bond starts to breaking up. What's going to happen? Carbon oxygen bonded more solidly. Carbon boron bonded slightly weaker because of the electronegativity differences. Therefore, further this carbon boron bond will be break up, and then carbon oxygen bond will be formed. So you can form a carbon hydrogen bond. This bond will be break up. This oxygen, this bond will be also weakening and then break up to produce hydroxide. So over this side, you are going to form an, we call the alkylcyborine. This bond is also subject to the cleavage. This cleavage is going to be under the water condition. Therefore, you call it hydrolytic cleavage. What does that mean? You have your water molecule. Water molecule have hydrogen positively charged end. That hydrogen positively charged end will be more attracted by the oxygen from this alkoxyborane. So hydrogen bonded with oxygen to form a hydroxy group. You form an alcohol, and the oxygen boron bond will be break up. oxygen boron bond will be break up. Your oxygen from your water will be more attracted to the boron. Therefore, you form another product. So again, your OH group will be replaced the oxygen boron bond. You form this a weak acid. So that's why you need a strong base to neutralize a weak acid during this production. So this reaction you can see, this is anti-Markov-Nikov's product. So let me go back. This reaction is called hydroboration oxidation reaction. This reaction produces a product which is not following the Markov-Nikov's rule. It's going to give you anti-Markov-Nikov's rule. This product is also form a trans alcohol. Trans alcohol will be produced. This reaction you need two steps. First step, you do need a hydroboration reaction, meaning your alkene must be reacted with borane. Second step, you must subject the oxidation reaction in the basic solution. That's you produce a anti-Markov-Nikov's product. Then the other reaction is halogenation. Addition of halogens to your alkene is called halogenation reaction. Generally speaking, your bromination, chlorination are commonly used. This addition reaction is also called electrophilic reaction. Electrophilic addition of halogens to alkenes yields vicinal dihalides, meaning you have double bonded carbon. Each of the carbon will be reacted with one halogens. So you form a vicinal halides, such as this 4-methyl, 1, 2, 3, 4, 5, 4-methyl 2-propene reacted with bromine in a solution with trichloromethane as your solvent at room temperature. You are going to produce 2,2,3-dibromo 4-methylpentane. This reaction has a one-direction favorable regioselective, and also you form a very high product yield. It's called vicinal dihalides. Vicinal dihalides. This vicinal dihalides, so it's subject to an anti-condition. Your hydrogenation, you're adding hydrogens, subject to syn addition. Your halide formation through halogenation is subject to an anti-addition. For example, if I have this cyclooctane, 8 carbons, so these 2 Cls adding to the double bonded carbon, they are in a trans position. Make sure it's stereoisomeric. They are going to subject to the stereo selectivity. So what's happening? We are going to show you called the back attachment. The addition reaction of your halogens into the alkene. Also, you are going to consider substituents. This isolene, no substitution. One mono, di, tri, tetra, etc. Your tetra substituents is going to result in a rapid reaction rate. Again, the more substituents you have, the faster the chemical reaction is. So let's moving back to the mechanism of bromination. If you have this cyclopentane, you are going to produce a trans 1,2-dibromocyclopentane. So why you produce a trans position? Again, this bromide is going to be attached to the carbon, which is a carbocation from the back side, from the opposite side to the bromonium. You form a bromonium, and then the anti-addition or trans product will be produced. For example, you have 2 steps. Step 1 called addition reaction. Step 2 called combination or attachment, called bromide back attack. Step 1, if you have your cyclopentane, you have your bromine. So this Br2 is going to subject to a heterolytic bond cleavage. So these 2 electrons is going to be retained by the bromide to form a negatively charged ions. And this Br is going to be bonded with carbon, double bonded to carbons. You form a 3 numbered rings. And this bromide losing electron, you form a positively charged ion. This one we call the bromonium. Hydroxonium, oxonium, you call the bromonium ion. This intermediate obviously is not stable. This intermediate charged positive ion is going to be attracted by the negatively charged ion. You call the back attachment. So this bromonium, so this intermediate is going to be subject to the back attachment. So therefore you form a trans dibromide. Again, you are subject to the anti-attachment, anti-addition. For your halogenation, for example, bromination, chlorination, you produce trans product. So that's a very important one. And about the halohydrogen formation, this is also the addition of your halogens, but in a different condition. You are going to have your water in presence. The reaction of your bromine with alkene in the presence of water is going to produce a vicinal halohydrogens, meaning one double bonded carbon will be bonded with bromine or bromine. Another double bonded carbon will be bonded with your hydroxyl. So this product, you call it halohydrogen. This molecule, you name it as alcohol. 2 carbon, you call it ethanol. You have a bromo as your substituent. You have 2 bromo ethanol. So this is your halohydrogen. This reaction is also a regioselective reaction. It's also subject to what you said, the back attachment of your bromonium. Instead of bromide, you have hydroxide. So this reaction, again, you are going to subject to the sterol selective and regioselective as well. You produce a very high yield halohydrogen. This bromide is just essentially considered as similar to your hydrogen, just considered as your hydrogen. So this is another important reaction. So the halohydrogen reaction we already essentially mentioned, you are going to produce an anti-product or trans product. So again, as we mentioned, that's you form a 3-numbered bromonium or chloronium, and then your hydroxide is going to attack from the back position. Again, you form an anti-addition. This is an anti-addition. OH and Cl, these 2 substituents, must be located in the anti-position, trans position, that position. That trans isomer is your dominating product. You have a 52 to 56%. Followed by, we are going to discuss oxidation reaction of your alkene. As we briefly mentioned, oxidation, you have 2 types. One is called epoxidation. Another one called ozonolysis. Epoxidation is going to result in a 3-numbered ring to form. So this 3-numbered ring substance is called epoxide. The epoxides are 3-numbered rings with 1 oxygen atom, such as if I have ethylene, CH2 reacted with your hydrogen peroxide, for example, you produce this called epoxyethane. This molecule is called epoxyethane, or you can call it oxide, called isolene oxide. If you have propane, double bonded propene, you are going to form 1,2-epoxy propane. If you have a cyclohexane, this 1,2 carbon form a 3-numbered ring, you call the 1,2-epoxy cyclohexane, or etc. etc. This is how you are going to form an epoxide. There is something for personal curiosity. This is called the dysperlyl. This is one of the female gypsy moth is going to attract it to the opposite gender for mating. So you can see this is a compound which is also an epoxide. How this epoxide is going to be formed? So what's the mechanism? The mechanism, again, we are going to learn something called a 3-numbered ring formation. So this reaction, you can make it this way. So your alkene reacted with your peroxy acid to produce an epoxide and another carboxylic acid. So you can think this way. You have a carbon-carbon double bond. This peroxy acid, one of the oxygen, will form a 3-numbered ring with this carbon-carbon double bond. So you form an epoxide, and then this oxygen is going to be removed. You are going to produce a carboxylic acid. For example, I have my, let's see, I have 12 carbons. You call the dodecane. This dodecane, number 1, number 2 carbon will form a 1,2-epoxy substituents. And then this molecule you call the peroxy acetic acid. This is related to acetic acid. You call it peroxy acetic acid. One of the oxygen is going to form a 3-numbered ring to form 1,2-epoxy dodecane. And then this peroxy acetic acid forms acetic acid. That's your chemical reaction. About the reaction rate of this epoxidation is following the same rule. The more substituents you have, the faster the reaction rate is. So this is some examples for you. The mechanism, again, you have something we call the 3-numbered ring to be formed, or you can somebody consider 5-numbered rings, but I essentially considered this peroxy acid compounds. This one of the oxygen is going to be attracted to the double bonded carbon, and then you form this 3-numbered ring as a epoxide. So the transition state, somebody considered you form from your peroxy acids, you form a 3-numbered ring. For your carbon double bonds, you form a 3-numbered ring. You form 2 different type of rings. So 3-numbered ring or 5-numbered ring for your oxidation state, for your oxidizing agents. That's how this transition state. This transition state is not stable. This carbon-oxygen bond will be formed. Oxygen-oxygen bond will break up. Oxygen-hydrogen bond will be break up. Oxygen-carbon bond will be formed. That's why you form your epoxy compounds. If you have a bicyclic compounds, you are going to essentially similar to form a bicyclic compounds. Another oxidation reaction is called ozonolysis. If you have your ozo as your oxidizing agent or reactant, this ozo triatomic allotrope of oxygen is known as a very strong oxidizing agent. Ozo reacts with your alkene, is going to form ozonide. This is called ozonide. You completely form a 5-numbered ring, and then this 5-numbered ring subject to the hydrolysis. This ozonide is going to be hydrolyzed in water to form 2 carbonyl compounds, and then this ozo becomes hydrogen peroxide. Typical reaction, for example, if I have 8 carbons, I have my 1 decene. What's going to happen if you apply ozone in the alcohol or cell? What's going to happen? These carbon double bonds will be break up. carbon double bond will form carbon oxygen double bond. Another carbon double bond will also form carbon oxygen bond. You form two carbonyl compounds. The first one, even though we don't require you to know it, but you need to know this name called heptanol. This heptane change ANE to AL, ANE to AL. This molecule is commonly known as formaldehyde. Similarly, you have another molecule. This is 2-methyl-1-hexene. This double bond also going to be break up. If you apply ozone in water, you must have water or polar molecule. So and then in zinc, you are going to form a hexanon, and then your formaldehyde. Again, when you subject to the ozonolysis, your double carbon double bond subject to the ozonolysis, you are going to produce two carbonyl compounds. And then I want to show you some examples. For example, I have my reactants, which is alkene. So I want to know how this alkene is going to be produced 2-acetone and 2,2-dimethylpropanol, meaning I'm going to form these 8 carbons. The first one you need 3 carbons. Acetone you need 3 carbons. Another one you need 5 carbons. How do you break it up? Where do you put the carbon-carbon double bond? One is 3, another is actually I should say 1, 2, 3, 4, 5. 1, 2, 3. So where you adding the carbon double bond? 3, 5. Meaning you need the carbon to be bonded in between the carbons. Acetone from this part. What you can do, you rewrite this molecule, you remove 2 oxygens. You adding this CH3, 2 of them, to this carbon. So therefore you have this molecule. Your molecule is going to be subjected to the carbon-carbon double bond cleavage. So you produce acetone and 2,2-dimethylpropanol. Again, this reaction is considered retrosynthesis. From your product, you are going to predict what is your reactant. And then we also want to show you one more point about free radical addition of hydrogen bromide. So before, when you're discussing hydrohalogenation, if Nikov's product, you simply adding hydrogen to the carbon with more hydrogens. This highlights to the carbon with less hydrogens. If you are going to adding peroxide, you are going to produce an anti-Markov-Nikov's product, meaning this Br adding to the carbon with more hydrogens. So this is another reaction of addition of hydrogen halides into your alkene. Hydrohalogenation can produce 2 types of reactant products. One is Markov-Nikov's product. Another one is called anti-Markov-Nikov's product. So these 2 reactions we need everybody to pay attention. So what happened? We are going to discussing free radical addition. In your peroxides, this peroxide is going to be subjected to the homolytic bond cleavage to form the radicals called alkoxy radical. This peroxide, this bond is weak. Therefore, this step you call the initiation. And then your hydrogen halides, hydrogen is going to be reacted with this radical. Hydrogen halides is also going to be subjected to homolytic bond cleavage. You form an alcohol and bromide atom. So this step you call the propagation continuously. So this bromide reacted with your alkene to form a radical. Again, the radical you need to determine which radical is more stable. Tertiary is most stable, followed by the secondary, and then followed by the most stable one is the tertiary, and then secondary. The primary is not stable. If it's not stable, you are going to subject to the rearrangement, and then this radical continuously adding with either with hydrogen or with bromide. So you have your hydrogen abstraction, and then these two steps keep repeating from step 2, step 3, 4, and step 2, 3, and 4 keep repeating. You also have the termination. If two radicals they reacted with each other, you terminated your radical reaction. That's generally speaking what's happening. This reaction again, your hydrogen highlights, so can form a Markov-Nikov's product, can also form an anti-Markov-Nikov's product. Depends on the different mechanism. If you have radical synthesis, you are going to follow the anti-Markov-Nikov's rule, but you must have peroxide in your system. The very last reaction will be our polymerization reaction. Commonly known polymer is your polyethylene. Polyethylene is a very important radical polymerization of your ethylene. So you produce a polymer under high temperature, high pressure. Also, you may need peroxide or oxygen as an oxidizing agent. This reaction again is going to go through the free radical formation. As we mentioned, your peroxide is going to subject to the homolytic bond cleavage to form two radicals. Those two radicals called alkyl-oxy radical. This radical will be reacted with your ethylene double bond. Further, you are going to, so this radical, this unpaired electron will be bonded with one of the pi electron. So they form a carbon-oxygen bond, This carbon retain one of the electron, you form a radical. And then this radical, this is called the 2-alkoxy-ethyl radical reacted with your ethylene. Again, this pi electron, one of the pi electron will be taken away by one of the carbon to form a carbon-carbon bond. The second pi electron will be retained by this end carbon to form a radical. The first one you call the initiation. Second 3 steps called the propagation. Propagation can continue, resulting in the enlarged chains. So the number of N in your molecule, so you can see this number of N should be in a certain range. It's not a fixed number due to the termination reaction which may occur. Another commonly known reaction is Teflon formation. Your Teflon is formed by radical polymerization of your tetrafluoroethane. You have your ethane, four of the hydrogens will be replaced by 4 fluoros. You call tetrafluoroethane. This Teflon normally is known as a non-sticky surface. So coated onto the surface give you a very non-sticky surface. And then we also gave you some other examples, something called retrosynthesis. This is something new, you may not know, but the reaction you should know. For example, I want to produce an epoxy. I want to know how this reaction is going to be produced, or how this product is going to produce. This reaction is going to occur. You are going to use this double arrow to represent the retrosynthesis. Retrosynthesis meaning from the backward. You know your product, you are going to predict your reactants and the related reaction. If you have this epoxy, what you are thinking? From epoxy, I'm thinking of alkene. From alkene, I'm going to thinking about epoxide. From epoxide, I'm going to thinking about, if you have this epoxide, go to alkene. From this alkene, I'm going to thinking about dehydration reaction. Therefore, if you were given the alcohol, I want to produce an epoxy compound. In that case, this alcohol is going to be subjected to the dehydration reaction. Dehydration, you form an alkene. This alkene will be subjected to the oxidation reaction. You form an epoxy compounds. This is another method called retrosynthesis. Followed by, I showed you several compounds, such as all of these different compounds of your alkene. What is the heat of the hydrogenation? The heat of hydrogenation essentially corresponding to the stability of the related compounds. The higher the heat of hydrogenation, the less stable, meaning that forward reaction rate will be faster. And also about the different addition reaction, such as you have your addition reaction of your hydrogen halides through the carbocation formation. So this case, what is the different step? What's the energy change? If you have your hydrogen halides addition, you are going to use the light go through the radicals formation. What's going to happen? One, you form a Markov-Nikov's product. Another one, you form anti-Markov-Nikov's product. So just want you to differentiate these two different types. And then the last slide, I show you several different commonly used polymers. Those polymers such as polyethylene, commonly used plastic. Your plastic bag, you go to H-E-B, Walmart, you buy your goods, you put them into the plastic bag. That plastic bag is your polyethylene, commonly used as packing materials. Also your squeezing bottles, but they do pose some health concerns. Your styrofoam, which is composed of polystyrene. So this one is very important for the radio or television cabinets, sometimes house wires, suitcase luggage for the coolers. And then the other one is vinyl chloride. This vinyl chloride, if you produce a polymer, you call the PVC. The PVC can be a very good replacement of your leather, so you can use it as tubes or pipes. And other ones such as this polyacryl nitrile. This nitrile can be a very good wool substitute. You can use as a blanket or use a sweater, etc., etc. Again, the last slide show you several commonly used polymers. So that's it for today. So today, up to now, we finished the alkene reaction. Generally speaking, 3 different types of reaction: addition reaction, oxidation reaction, and polymerization reaction. So you are going to know carbocation formation, radical formation, and also you need to know 2 rules. One is called Markov-Nikov's rule, another one called anti-Markov-Nikov's rule. That's all for today. Thank you so much. Stay safe and stay healthy.